Hi, I'm Brandy Heflin. I'm a personalized physics instructor, and I help high school and college students feel confident and successful in learning physics. I'm here today with a solution to a very typical beginning physics problem that involves finding the tension between two boxes in a string of boxes that are tied together and being accelerated by a force. Problems like this even show up on the National Physics exam, so while I will walk through a couple of specific solutions, I will also show you a general solution. We will also work this problem with friction after demonstrating the solution without friction, and we're going to use one of my favorite tools, which is systems thinking. So this very typical problem has a series of boxes that are tied together like this and being accelerated by a force. We are going to let F be the force that's accelerating the boxes and let M be the mass of each box. Assume there's no friction. So let's figure out how to solve this problem for the last box. Let me go ahead and make sure that my tool is turned on. The first thing that we're going to have to do is find the acceleration of this entire system. So we have this force F that is pulling three boxes, each of mass m. And so we're going to think of this as one complete system that's being accelerated by this force. This force, whatever it is, or whoever's doing it, doesn't know if they're pulling three distinct objects, each of mass m, or one big object of mass 3m. So to find our acceleration, we will do the net force on our system divided by the total mass of our system. And obviously, vertically, the forces are balanced because there's no acceleration that direction, and it's only in the horizontal direction that there's an acceleration. So I'm not going to worry about those vertical forces. So the force F is what's accelerating our system, and all three masses are being accelerated by this force. So symbolically, we can say that our acceleration is equal to F divided by 3m. So now, all three boxes are going to be accelerating at that rate because they're all tied together and moving as one object. So now, to find the tension between boxes, I should have labeled them 1, 2, and 3. Let's find the tension here in between boxes 1 and 2. We're going to consider the fact that that rope is accelerating only block 1. So I'll go ahead and write that. So the rope between boxes 1 and 2 is accelerating only box 1. So when we then apply Newton's second law just to box 1, we're going to get, I'll call it FT1. Let me go add a 1 there. Is going to be accelerating just this single mass m. And then we have our acceleration F over 3m. And we will get that our tension is equal to that pulling force divided by 3. Now let's solve the problem considering the tension here. We'll call it tension 2. That's going to be accelerating just these last two boxes. So the acceleration of the system is the same because we haven't changed the force that's pulling the system, nor have we changed the masses of our boxes. So our acceleration is still going to be F divided by 3m. And Now we're just going to apply the net force on 1 and 2 to just those two boxes. And again, this guy was M1 and this guy was M2. They do happen to be equal to the same mass M. So we've got that tension 2. Again, tension 2 doesn't know, is it pulling two individual objects, each of mass M, or is it pulling one big object of mass 2M? So we can actually exploit that. Here. All right, and so the M's cancel, and I'm going to get 2/3 F is the tension. So this makes sense, is that, you know, the force needed to accelerate only part of the system, only a couple of the boxes, of course, is going to be less. So now let's generate a general rule. What if instead of 3 boxes, I have N boxes? Well, we're still going to have our pulling force F. You know, maybe there are a whole bunch of hidden boxes here that are just not drawn in this diagram. So we can still apply, you know, net force equals MA to our whole system. Well, our net force is the pulling force F, and then we're going to add up all of the masses of our system for however many there are. So our acceleration is just going to be our number of boxes N times the mass of each box M. And of course this works like this because each box has the same mass M. You know, our general rule would be a little bit more difficult if we had boxes of different masses. So now let's consider the tension between box N, which is the front one, and box numbered N-1, which is the second box in the string. This is the version of the question that has shown up on the National Physics exam before. So let's pretend that we have a whole lot more boxes back here, and let's just worry about this. So we'll call this FTN-1. So we'll still apply, you know, we're still thinking about Newton's second law for our system. What is our system here? Well, we're going to have that tension on box N-1 is going to be equal to that mass plus all of the masses behind it, which notice when we had 2 boxes, that coefficient was 2. If we had 3 boxes, it would be 3. Since we're considering N-1 boxes, we're going to have a mass, total mass, of N-1 times M, because M is the mass of each box, right? M is the mass of each box. And then our acceleration is our pulling force F divided by N times M, and we get a general rule of the tension that's pulling the second box in line will be equal to N-1 times F divided by N. And I encourage you to try this. Go back to those previous examples where we're working 1 box and 2 out of a string of 3. What if we had 4 boxes and worked a string of only 3 of them? What if we had 5 boxes and used only 4? So test that out and find out, does this rule apply? So now let's consider this problem if there is a friction force between each box and the surface. And since we know friction equals coefficient of friction times the normal force, and with no vertical acceleration, the normal force will be equal to the weight of each box, we can say, and then each box has the same mass, we can say that each box is going to have this frictional force, lowercase f, acting on it. So we're still going to look at our whole system here to get our acceleration. And again, the point of circling our system is that we're considering objects inside the system, inside the circle, are part of the system. Anything outside is not a part of the system, but can interact with the objects inside the system. And so in this case, that surface is outside the system, but can still interact with the boxes. So I'm going to go straight for, look, acceleration equals net force divided by mass. So each box has an interaction with the surface. So friction gets subtracted 3 times, 1 for each interaction. And let's fix that. There we go. And so our acceleration will be capital F, the pulling force, minus 3F for friction divided by 3M, the mass of our system. So I'm going to show you 2 things here. First of all, what if we just deal with, we'll call it FT1, acting on just that block. We numbered this one 1, this one was 2, this one was 3, by the way. So we'll do tension 1 minus friction, again, no vertical acceleration, only horizontal, equals its mass multiplied by the acceleration we found before. And the m's will cancel. We'll add a lowercase f to both sides, and the tension for block 1 will simply be the pulling force F minus 3 times the frictional force, all divided by 3, and then add in that lowercase f for friction from the other side. And what if we worry about these 2? And why am I showing you this? Because there are AP Physics exam questions that ask students to work problems very similar to this, and all symbolically as well. So the net force on our system of 1 and 2, again, we're going to have both of their masses involved. And in this case, we're going to have 2 frictions subtracted. Oops, let me just fix that. I could just write 2m for that, make it easy. And then we're going to have f minus, oops, hang on, let's try 3f. And divided by 3m here. And so we've got tension minus 2f equals, really we're going to have 2/3 of f minus 3f. And let's add our friction from the left side, and we will get a symbolic result for the amount of tension that's pulling the last 2 blocks in the chain. So I hope you have enjoyed this explanation today of how to solve this very typical beginning physics problem. If you have additional video solutions that you would like to request that I put on my YouTube channel, you can send them to physicsproblemrequests@gmail.com. If you would like some additional email assistance, you can use freephysicshelpline@gmail.com. There's a limit of 10 questions per academic year. If you want to learn more about my physics tutoring services all online, you can email me at bradyheflinphysics@gmail.com. You can visit my website, virtualphysicsofficehours.com, or you can find me on Facebook. I'm Physics Tutor Brandy. I love physics, and I love helping you. Until next time.